So this is kind of like a dense chapter, and I feel like I missed a lot of the previous like learning seminars. So I kind of wanted to start at like the ground up, but here I have a presentation, and then I have a little bit of an example afterwards. So, okay, we'll just start off with, so the project is on graph neural networks or graph convolution networks. So I want to start off by talking about what an actual neural network is and how they're different, and when you might use a graph neural network instead of a neural network. But so I'm sure many of you are familiar, or like all of you are familiar with what a typical neural network is. So it takes an input of nodes, which in our case is a vector, and it applies a bunch of linear transformations. Each neuron is connected to every neuron in the previous layer, and we multiply by a weighted sum. We run it through our activation function, which is ReLU. So we end up getting like a summation of nonlinear functions. And so basically, a neural network allows us to predict a function based on input. So ultimately, we're mapping input to output with a neural function. So this is a video showing how it might learn. And so a couple important things are like backpropagation or minimizing loss. So as the neural network grows, we have more of these neurons, more of these functions. We can represent more like complex functions. And the more iterations we get, the better the model can learn. And ultimately, it's just really minimizing loss to represent like some function. So key characteristics of traditional neural networks. The input vector is really, the input is really a vector with n features.
Luca, can you make it bigger?
I don't know. I don't know. Do you know? You use
I think it's command plus Mac,
that zooms in. No, this is a HP window.
but there should be a way to, if you go to the, is this in a browser or?
This is a GitHub code spaces.
Yeah, I think there should be something to zoom.
To full screen GitHub code space. Control Shift D.
That's,
That is
yeah.
Did I get it? Oh. Okay. I mean, this is as good as we're gonna get, guys. No, I don't know. I don't know. But I can zoom in like this. So this is
Okay, bigger, even bigger.
this is our neural network. So yeah. So this is it learning over like a bunch of different epochs, which is just like a training layer almost. So okay, yeah, key characteristics of a traditional neural network. So the input is really a vector with n features, and hidden layers can really have any combination of nodes. There can be any amount of hidden layers, but for a graphic neural network, that is gonna like affect the output as I'm gonna get to that, but like there's something called data smoothing. Okay, for now, let's just focus on this. So the output can be of the same dimension, but typically, like a neural network's goal is to reduce the number of features. So if the input is, going back to this, if the input is 3, like a vector of size 3, like it can be, the output can be a vector of size 3, but typically we want to like reduce the number of features to classify it like yes or no. So like in a regression problem, we want to have one value, which is like a scalar representing maybe a probability, or if it's a yes or no, it can be a 0 or 1. And typically it's still like a range of values. Like it can say, oh, it has a 0.6 probability of being yes, and it's gonna say yes anyways. So yeah, so for binary classification or regression, the feature output would be one-dimensional and calculated differently than multi-class problems. So why graphs for complex problems? So let's consider these two problems. So imagine we want to look at a molecule and determine if it's poisonous to humans based on the structure. And another problem is at what temperature will this molecule change phase? So these are two, like the output should be one dimensional. So we want to take a graph and we want to say yes or no, is it like toxic to humans? And then like the converse, like the regression problem would be what temperature does this molecule change phase or like, start melting? Like what temperature do the bonds break? And so with a standard neural network, as I just explained, we might pass in the elements as an input, but the network is only going to learn like the relationship between maybe the proportion of the elements. So it might flag like, oh, there's halogen in this molecule, and that makes it more likely to be toxic. But I mean, if you've taken chemistry, like the most important part of a molecule is really its structure. And so the elements do play a big role in the structure. So this is where graph neural networks come in. So if we represent a molecule right here as a graph, then we can start to see how elements really interact with each other and create a larger structure. And ultimately, we want to recognize patterns, just like in any neural network. We want to recognize patterns and like see what's contributing to a molecule's toxicity. So if we represent a molecule as a graph, then the edges are the bonds and the nodes are the elements. So for our graph neural network input, each node is going to have a vector associated with it. And so for our problem, this is going to be a one-hot vector. So there's 118 elements in the periodic table. So it's going to be populated with all zeros except for a 1 where like signifying the element. So I think hydrogen is the first periodic element. I'm not sure, but okay, it is. So then it would be like 1 and then 117 0. So that's what each, so this is like an example of our input. So instead of like a 5-dimensional vector, this would be 118 for our problem. And so some important things to note is that when you have a graph like this, nodes have information, edges have information. And we can represent the connections between nodes as an adjacency matrix. And I made some code for an adjacency matrix, and if we have time, we can look at that. But for now, so like looking at this, right? There's a connection between 3 and 1. So if we look at 3 and 1, this is filled in. Or in a real matrix, this would be 1. And like a gray value would be 0. So do 2 and 1 have a connection? No. So 2 and 1 is blank. And like we can do this for all of them. 3 and 6, there's a connection. So this is filled in. And some key things to note is that it's symmetric. Because when we have a connection between 3, 1, we have a connection between 1, 3. And
so how about if the graph is a directed
exactly
graph?
So it's only symmetric when it's undirected. So if it's directed, it would just lose its symmetry. You can still represent it. So it would be like if it's a connection from 1 to 3, this would be filled in and this wouldn't. But if you want to like efficiently compute, so there's a couple interesting properties about adjacency matrices. So like obviously on this graph, if it's filled in, there's a walk of length 1 between the cities. So if we look at 3 and 1, it's filled in, so there's a walk of length 1. If we square this matrix, then this is filled in if there's a walk of length 2 between these cities. So in this case, this would be filled in because we can walk from 3 to 4 to 1, which is a walk of length 2. And the math of it makes sense, but the book doesn't really explain that. And it's not really important to our problem. I just think it's interesting. So we also represent the node data as a matrix and the edge data as a matrix. And they can all have different dimensions. So the node data in the adjacency matrix are going to have the same column, but the edge data is not, So, but this is the input to our graph neural network because a computer has trouble like understanding this. So basically, it's not too complicated. This is just our input, and any graph can really be represented with these 3 things. So graph convolutional network. To classify an entire molecule into a single value, we can use a graph convolutional network. So similar to a neural network, the GCN has layers, but the key difference is that GCNs consider information from neighboring nodes. So this means we're learning the context of an element within a molecule and its relationship to other elements. So last seminar, Shende talked about natural language processors. in how we don't really care about the definition of a word. Like if we have the word machine, we care about the context of a word. So machine learning, right? That has a totally different meaning. And in a transformer, we represent that as vectors and with closeness. But in this context, we really do the same thing. Yeah, we have vectors to represent the information. And yeah, I mean, there's a lot of layers of abstraction, but we're just trying to figure out how elements fit together and how they have like, how they contextually fit into the molecule. So if that doesn't make sense, our first layer of the GCN. So for every node is going to do this, by the way. So looking at node 3, it's going to see what is my neighbor's value? What is my neighbor? So it has 4 neighbors, right? It's just going to say, what are my neighbor's values? And it's going to consider this. By consider, I mean, it's going to pass these into a neural network. So another neural network, or the only neural network, because a graph convolutional network is relatively similar, but this is the difference right here. So it's going to say, what are my neighbors doing? Like, how are they similar to each other? How am I similar to them? Like, what is this connection? It's going to look at its own vector, of course. Okay, and I should say it aggregates its neighbors. So most algorithms just take an average. So it maintains the dimensionality of the vector. So which is, it's intuitive. So if we have a 5-dimensional vector and we add it, all these 5-dimensional vectors and divide it by 5, we're just gonna get an average of like the neighbors. So we consider that new vector with its own, we pass those into a neural network, or we linearly transform them to kind of get a new vector. So we get a new vector for each node. So by layer 2, node 3 is gonna have 1 vector again, right? So we're gonna get this context vector, and we're gonna get this like original vector, and we're gonna kind of see like, what's the context? Like, what does, this is an atom, right? Or an element in our case. So it's gonna say, is this just a hydrogen, or is this maybe a hydrogen chain? Maybe is it connected to other hydrogens? And is a hydrogen chain dangerous? Is ultimately gonna be like our prediction, right? So every node is gonna do this. So on layer 1, this node is gonna have context, this node is gonna have context, this node is gonna have context, right? And so some important things to note. So in every layer, a node is only gonna grab from its layers. So you may that may be confusing because you're like, how is it really gonna learn about outliers that it's not connected to? Because it's just gonna be like an information loop. It's gonna keep taking information from the same ones. But so it's almost like an inductive proof. Imagine on our second layer, we grab information from 4, and we consider this in our node 3. Well, in the first layer, 4 grabbed information from 5. So in our second layer, 3 has really grabbed information from 5, and it's traveled 2 edges. So this is how I was talking before about how layers play an important role in the GCN. So the data transfer is upper bounded by the number of layers we have in our GCN. So if a GCN has 3 layers, it's going to grab 1, 2, 3 nodes away. And I kind of illustrate that. So, okay, layer 1, each node connects information from its neighbors. Each node sends out its own information. Each node updates its internal state using a neural network. This process is a linear transformation that reduces dimensions and recognizes patterns. These transformations use weight matrices that can be learned during training. So this is going to be the start of our second layer. And you'll see each node now has a new vector with reduced dimensionality that kind of, it's telling now about its context and the surrounding nodes as well as its own. So it hasn't really lost its structure or its own meaning, because we have to consider that when we pass it into our neural network. But this is going to be the input for our second layer. And of course, we're going to do the same thing. I kind of show it. Yeah, I show it here. So if we grab information from 3, the drawing may not be the best, but we're grabbing it from 2, 1, 4, and 6. And on the first layer, we grabbed it from 5. So ultimately, we're grabbing information from every element.
Would it double each time?
What do you mean double?
In the second layer, you know everything about things that are distance 4 away.
Yeah. Oh no, it wouldn't double, it's linear. If you have 3 layers, you can like look at 3 nodes away or 3 edges away. I mean, it's like it doesn't seem the most efficient, and there's other ways to handle this. So like you'll kind of see like, well, 4 has learned about 5, and 1 has learned about 4. 3 is going to learn about 4 in 2 different ways here. So data is kind of going to get smoothed out, and we're kind of going to lose some meaning unless we like are intelligent about how we gather data. So ultimately, every element is going to be a 1-dimensional vector. That's our goal. So like this is like an abstracted layer, right? So in an ideal world, what our algorithm might be doing is the first GCN layer, we're going to recognize pairs. We're going to see maybe H2O is together. Maybe that's a significant thing that appears commonly. Maybe HCl, or I don't really know chemistry, but you know, there's a bunch of different, and then so another layer might see, oh, there's a hydrogen chain. Oh, there's a carbon chain. Oh, if there's 2 like hydrogens together, that's, you know, that's a pattern that occurs. Our final layer is finally going to say, oh, when there's a carbon chain and a hydrogen chain, maybe that makes it an acid, and that's definitely toxic to humans.
So a priori, how do you, I mean, suppose you are given a problem, but how do you come up with this graph? I mean, there's different graph, different relationships. How do you come up with a graph?
So when you're talking about relationships, you mean like the edges? Like
Yeah. So I mean, like this specific problem that you talk about, is all these elements, they want to decide whether it's harmful or not, some chemical. So how, but then that means that when you each layer is defined by the graph, am I right?
Yes.
So how do they come up with what kind of graph? That those are from chemistry or how?
Oh yeah. So I use we can get a sneak peek, right? So this is so we just like, this is how we would represent it in a computer sense. So we use a database that's provided by PyTorch Geometric Molecule Net. So yeah, it's chemistry. So these are the different like categories a single molecule can belong to. It can be a nuclear receptor, androgen receptor. There's a whole bunch of stuff. Tumor suppressors. So this is the stuff we're really looking at. But going back, so yeah, like relational graphs is a whole different problem. So because like you don't want to just average your neighbors when they have different relationships. Like let's say this is a social media network, and user 3 blocks user 1, but user 3 loves user 2, right? They're both neighbors, but we shouldn't add these vectors together and sum them. We should say, oh, this is a friend, maybe we like this better. This person is blocked, maybe we don't like this person. So we want to understand the context differently. So relational graphs are a different problem, but it's an extension, and it's something I do want to cover, because in a molecule you can have covalent bonds, ionic bonds, double bonds, and that really should change like the output. But that's a conversation for a different day, I guess. So ultimately, this is our last layer. So each node has now been represented as a 1-dimensional vector. So we have taken 118 dimensions and we have reduced them to 1. And ideally, this is saying like what the element is, what its context is. Is it part of a chain? Is it part of a structure, you know, etc. So our node data matrix now looks like this. It's a 1 by n. And ultimately, if we want to classify this graph, we're just going to average these, run it through a final neural network, and put it through a sigmoid function, so we get an output between 0 and 1. So if we apply like all this context to our problem, so each node, oh my God, I gotta stop doing that. Yeah, okay. So each node's vector is 118 dimensional. So we collect and aggregate the neighbor data for each node. We process this aggregated data through a linear transformation. So aggregation typically means summing the neighbors' vectors and taking their average, but there are multiple ways to accomplish this. And so we process the node's own vector and its neighbor's aggregated vector through a neural network or linear transformation with learned weights. So that's what we're tweaking. We're tweaking like how it interprets the meaning of these vectors. This typically reduces the dimensionality, creating an abstracted interpretation of the element and its molecular context.
And the output is going to be a number between 0 and 1?
Ideally, that's the entire function. If we wrote it as a function, yes. We have f of x. So I kind of get into the math later, but yeah.
What's the edge matrix doing, the edge data?
In this problem, it doesn't mean anything, but if these were roads, right? Each road has like a length, it has a speed limit, you know, each city has a population. So I didn't get to cover this, and chapter 13 does go over edge graphs, where this is, instead of looking at the nodes, we would do the entire opposite. We would just look at the edges. So we want to understand the relationship instead of just the individual nodes.
I have a question. How many layers does it have?
My one has 3 layers.
No, but in general.
In general, it can have whatever. So like, if long distance connections are important to your problem, you want to have more layers. So imagine in a real world setting, you have 1,000 nodes, right? And a node on this side and this side, you want to like see how this node is affecting this, even if it's going to be like small. Then you would want 1,000 layers, right? So that it can reach this, because it's a linear like scaling. Like you want to, so like for certain problems that's not going to matter. Maybe social networking, you want to consider who's closest to someone, but maybe in a molecular problem, you know, like we do want to consider how every node is affecting this one node. So it can really get complex.
So the Google Map is using this web neural network. I mean, when you want to get from one point to other point, I mean, these edges would represent the speed limit or whatever the construction or those kind of information.
Yeah, you can definitely do that. I think they use Dijkstra's algorithm, which is like simpler. But if you want to learn more about like patterns or like how many people are traveling from one city to another, yeah, like you could definitely apply stuff like this. And I'm gonna cover like the problem spaces that we typically, so we already talked about this. I'm gonna skip this. So going to like the problem spaces. So there's so many graph problems. So some common examples are cities and roads and flights, social media networks where connection is a friendship. Images can be thought of as graphs, so can 3D shapes or point clouds. So maybe you have like a point cloud representing an airplane. This is an example from the book. And you want to like classify each atom, or no, like each point as maybe part of a wing, part of a fuselage, part of a, you know, airplane part. So then you could apply a neural network and you would classify each node, because each node would be a point. And the overall graph, we don't really care. We know it's an airplane. So we want to classify each node. And then our problem, the molecular problem, is a graph classification problem. So we're looking at the entire graph. We're saying, what is this graph? Maybe we're inferring something about it. Node classification, we're inferring something about the nodes. Edge prediction, I mean, I don't know why the book, so like they only mentioned one edge level task, which is to predict whether or not an edge is likely to be present. So in a social media network, if someone has a lot of connections, they should, and they're not following each other, it's gonna say, yeah, you guys should follow each other. Like, but there's way more you can do than just edge prediction. But you would use a graph neural network for that, and that would be an edge level task. So I haven't really got too far into the math, and I don't really want to, but this is what a graph level problem output is going to look like. They were saying what is the probability that y equals 1? So there's a classification. So like, what is the probability that this molecule is toxic? So here's our sigmoid function, which squeezes it between 0 and 1. This is our bias. This is our final layer of nodes. And this is our weight matrix. So we're really, as we saw before, these are going to be like one dimensional. So we're pretty much just averaging them. We're running that through a neural network and squeezing that value, that output between 0 and 1. So this is a node level problem. It's pretty much the same thing, except we're not averaging them. We're just summing them and putting it through a sigmoid function. So then we go back and like look at what the nodes actually mean with our output. And then edge prediction is another probability, which is, I'm not too sure about what this is actually saying, but H of M is the final layer. And okay, let's read it. The network predicts whether or not there should be an edge between nodes N and M. For example, in the social network setting, the network might predict whether two people know and like each other, and suggest that they connect if that is the case. This is a binary classification task where the two node embeddings must be mapped to a single number representing the probability that the edge is present. One possibility is to take the dot product of the node embeddings and pass it through a sigmoid function to create the probability. So we're gonna run our neural network, our graph neural network, our output, we're gonna take, so let's say we want to compare city 4 and 5, or I guess 2 and 1. We're gonna take their node embeddings dot product, take the dot product of them. We're gonna run this through a linear transformation, and that's gonna give us our probability. But ultimately, we're almost doing the same thing for each problem. Like our GCN just wants to learn about patterns so we can apply them. So in adjacency matrix, we already covered that, but it's important. So this is the map of what a layer actually looks like. So the first layer is just a function that takes our node embedding matrix, our adjacency matrix, and our parameters, and it returns a hidden layer with like n nodes. And we do this, for however many layers there are. And so this is what this looks like. So an important thing in
What is each of x? Of this x function, what is the?
this is like our neural network. So this would be our weight matrices sigmoid function, like the bias. That's really what this is doing. So it's like learning to create our new hidden layer. So that's what this is gonna look like. And we talked about this before, like each node is gonna have a new meaning depending on its context for each hidden layer. And so this is important. We also talked about this. So this is the aggregation of neighboring nodes written as a summation. So NE of N is just the neighbors. So we're saying for every neighbor of N, find the hidden layer. And we can write this as our sigmoid function bias plus a linear transformation of the current layer plus a linear transformation, or so the current node, like this is the node embedding of like say 3, and then we're looking at a linear transformation of our aggregation. And you'll notice these linear transformations are the same. So we learn those over a lot of iterations. So the nth column of this is bad format. I didn't even notice that. The nth column of the adjacency matrix contains 1 at the positions of the neighbor. Hence, if we collect the node embeddings into the D by N matrix HK and post multiply the adjacency matrix, the nth column of the result is the aggregation. So we're taking this equation for a node embedding, and we're just changing the way we calculate the aggregation using like clever adjacency matrix math. But ultimately, they're saying the same thing. We're looking at the aggregation of the neighbors with the linear transformation of itself. I don't want to get too bogged down in the math, but yeah. So this is our function for each hidden layer, and so we're gonna have all of these different weight matrices, all these different biases, but the adjacency matrix is ultimately the same. And so this is our first node embedding as input. This is our hidden layer 1 as input for our next. So you can kind of like, if you think about it, it's really gonna grow with all the context of previous iterations, just like a natural language processor. So you read a sentence left to right, and you kind of learn what the machine reads the sentence left to right, and it like a human, and it learns the context of what it's saying before. So ultimately, we're gonna have a lot of I don't know. Don't know what I don't know. Are we following? Is this a good explanation?
So the adjacency matrix is the same for each layer.
Yes.
Coming from the graph.
And I didn't get to touch on it, but there's permutation invariance in these hidden layers. So if we have our graph 1, 4, 5, 6, 3, 1, this one could be any number. We can permute these names anyway, and the relationship and our insights about the graph are going to be the same. So this could be a 4, 1, 3, 2, 6, 5, and our insights are still going to be the same. So if we had a P here, which would be like a permutation matrix, we would have a P over here. So that's one thing. So this is more like this is more problem spaces. So our problem is inductive. So we're looking at previous molecules, we're recognizing a pattern, and then we're trying to see, like we're looking at new molecules and trying to classify them. Whereas a transductive problem would be, this is a social media network, for example. Oh, no, let's say these are citations. Like this is each node is a publication, like a research paper. And if it cites a node, then they're connected. And each node is also going to have a vector representing what category it belongs to, like history, computer science, art, and then, so these are going to be classified. But what if we have unlabeled data? What if someone just publishes a new research paper? We don't know what it is. We're going to see what it's connected to and make a reasonable insight about what it might be. So that would be transductive, where we have incomplete data and we want to make inferences about that data. And so you can imagine in a real world setting, this transductive graph would be humongous. So this is where we apply like clever techniques so the computer can understand it. So yeah, we talk about batching here. So graphs in a batch are disjoint components of a single larger graph. So I don't think I have the picture, but in this graph, it's like clustering. So we would have, maybe these are connected, which is one subgraph, which is connected to these, which is one subgraph, which is connected to these, which is one subgraph. And so you're gonna infer about the relations of these subgraphs really after you've clustered them. But this here is neighbor pooling. So we want to get like a manageable subset of our larger graph and then make inferences about that so we can take that to a larger graph. So we choose one point, we zoom out a little bit, we zoom out a little bit more, and that's pretty much our new sample. So finally, yeah, you really do. So if you want to focus on one particular point, so like in a social media network, you want to look at, maybe you would look at one user, right? Because you don't want to like do matrix computations on like a million by a million matrix or graph, or matrix, I guess, adjacency matrix. You want to look at maybe one user, find out about them, and then find out about their network. So here are different types of aggregation. So we have our typical mean aggregation, which is the average of the neighbors. We have Kip's normalization, which so if you think about mean aggregation, everybody gets a fair vote. So like if a node has 1,000 neighbors, each one gets a fair vote. But if a node has one neighbor, that information is going to be almost amplified by 1,000, just because it's just one node. So Kip's normalization is basically giving like a distribution to each node so that we can have equal weighting. Because in a real problem like ours, one halogen element could make a molecule toxic, and that only has maybe a few connections. So we want to look at these like sparse inputs and be able to recognize patterns. So that's when we would switch up our aggregation method. We also have max pooling aggregation, which just looks at the maximum from the neighbors. So that's kind of going with like graph attention. So we want to see who's the most impactful to our neighbor. Like like who's the closest friend to this person? Who's going to influence their following the most in a social media context? So then we have aggregation by attention is creating weights of neighbor importance. So maybe these three friends are best friends. They're most important to this specific user. These other people don't really matter. So ultimately, the goal is to promote critical analysis in our model. So graph attention is realizing, what connections are most important to a predictive outcome. And so this is the end of the presentation. We have some graph attention here. So we have our input and they explain it. If it's not too zoomed in. So this is a comparison of graph convolutional network, dot product attention, and graph attention networks. So the mechanism maps n embeddings of size d in a matrix X to an output of the same size. So the graph convolutional network applies a linear transformation to the data matrix. It computes a weighted sum of the transformed data where the weighting is based on the adjacency matrix. A bias B is added and the result is passed through an activation function. So basically, the attention is learned because we don't exactly know, we can't really quantify importance before we understand the full problem. So we're learning these weights of attention for like the most important neighbors. So that was for this one, a graph convolutional network. So this one is dot product self-attention. And it says the outputs of the dot product self-attention mechanism in the transformer are also weighted sums of the transformed inputs. But this time the weight depends on the data itself via the attention matrix. And then lastly, we have the graph attention networks combines both of these mechanisms. The weights are both computed from the data and based on the adjacency matrix. And here we have like soft, I think we're normalizing the attention values, but this is towards the end, so I didn't really get to give like too much time to this. So that is my presentation. And now I want to give a demonstration of what this would really look like. So this is our graph convolution network using PyTorch geometry. So the problem, I mean, we've already looked at this enough, but for other people, like the problem we're working with is the molecule problem. We want to classify if it's toxic or not. So our model is only as good as our data. So the first step is to find a reliable data source with for our hypothesis. So PyTorch geometric, it comes with molecule net. Like this is a problem that's being researched today, like with way more complex models to represent this. Because I mean, like this stuff is important. Like we want to maybe gauge potential side effects of a medication, see if a medication, I mean, if it works, it works. But we also want to gauge potential risks without doing a lab test, without like doing experiments. Like we can let a computer do the work for us and recognize patterns that might indicate potential toxicity. So here we import all our libraries. We're using PyPlot for graphs. We're using PyTorch for our model and PyTorch geometric specifically for our GCN, our graph convolution network. So this is just loading the data set. And as we clarified before, this is just for like readability and labeling. So we just want to see what molecules belong to what category. So if we run this, it takes, this is not a good sign. It should really take like 2 seconds, but okay. We loaded our data set. So now we want to visualize our graph structure using PyPlot and Network X. And I don't want to get too bogged down in this either, but this is where we create our graph. This is where we like color the molecules. This is where we create an actual graph using Network X. And this is just grabbing like a small portion of our data set. So if we run this, we have two molecules here. There's a small mistake. These are actually the identical molecules, and it labels one as non-toxic, one as toxic. But that doesn't really matter. I'm going to change that soon. But this is what it actually looks like as a graph. And so this is what we've done so far. Like our data set typically uses, I think, SMILE representation, which is it's like a confusing notation to represent a molecule. So a graph is much easier to understand.
So you're saying in this data you got running it once, it was telling you it's toxic, and running it again, it's telling you it's not toxic.
So we're just pulling. We have classified data. It's already classified for us as toxic and non-toxic. So what we're trying to do is just grab one that is toxic, grab one that isn't toxic, and it just doesn't work correctly. So I'm gonna fix that. But so our next step is to define a loss function and our graph convolutional network. So loss functions are obviously important. They're integral to like the entire network and how it learns. So a loss function is essential for the learning process of a neural network. It quantifies how far a model's predictions are from the ground truth values. So the optimization process, we can call it gradient descent, we can call it stochastic gradient descent, or simply loss minimization, aims to find the parameters that yield the lowest possible loss. So in 3-dimension, in 2-dimension, we saw that like the sine wave before, we're trying to fit that and minimize loss. In 3 dimensions, we have like a topology, like a loss function with 3 dimensions. So for like x, y, z, we're gonna have a certain loss, and over here maybe it's higher. So the gradient is multivariable calculus. So it's finding what changes are going to make our ascent most rapid. So if we take the inverse, which is gradient descent, we're going to say what steps can we take from our vector that's going to make our loss descent as rapid as possible. So we can like imagine like a ball rolling down this 3D graph we have. So we also have to introduce our graph convolutional networks. So this stuff is all PyTorch. When you construct this, you just inherit a given module from PyTorch. So this is our GCN. We define the input dimensions, the hidden dimensions, the number of tasks, and the dropout. So we also have to define, we always have to define a forward, which shows how like a layer interacts with the previous layer. And again, I don't want to get too bogged down in what this is all doing, but like this is our class weighting, this is our like, we have masks, we have more weighting, and we also have data cleaning. So in our data set, a lot of the values aren't even labeled. And so we want to ignore those for the most part. And also in our data set, there's way more non-toxic. So like the first time I did this, there's way more non-toxic than toxic elements, almost like 99-1. So the model was like, oh, I'm 100% accurate, but it was really just guessing non-toxic for every element. So it didn't learn anything. So we're giving toxic examples 10 times the weight. So we're saying when you have give them more attention. Like look at these toxic examples more than just non-toxic examples. So we run this, that takes 0 seconds because it's just class definitions. So next we have our batch preparation. So this is where we transform like the data into tensors for our neural network processing. So for graph data, like we have this was another problem. So like a molecule can be two connections, two elements with one connection between them, or it can be like a crystalline subs, you know, like 30 connections, maybe 50 elements, like huge chains. So like, how do we really give those the same weight? And so we kind of use like padding to ensure that they have the same amount of atoms and bonds, so that our network can really better understand each one, or like what really makes a molecule toxic. So here we say aspirin has 21 atoms, 21 bonds, caffeine has 24 atoms and 25 bonds. And a protein-based drug might have hundreds of atoms. So we kind of want to normalize our data. And so this is what batch preparation is really doing. So we're assigning our features, we're processing our data here, we're making sure the dimensions are the same, and we're creating our tensors. So let's run this. And so first we want to make sure, before we train our model, we want to make sure the data is actually good. We want to see how much data was unlabeled, how much data is toxic, how much data is non-toxic, before we even do anything. So we pretty much just iterate through our data set, and we just look at everything I mentioned before. Like, is it missing? Is it toxic? Is it non-toxic? So we can run that too. And this is what it says. So it indexes through our list. And this, so out of 5 molecules, 4 had missing weight. So this takes a small batch. And this is what we were talking about before with like batching. So we're just looking at a small part, and we're saying that represents the entire data set. So 16% of the data is missing, 7% is toxic, and 92% is non-toxic. And so this is where the magic really happens. So we initialize our model class, our criterion, which is our loss function, and our optimizer, which is how it learns. And epochs are the number of iterations that we're going to learn over. And we have our batch size. So this is our main training loop. So for the number of epochs, we train the model, we find the loss. We find like the average loss down here, so that we can quantify this epoch had this much loss, and that's where we maximize it. So without getting too far into it, let's run it. Oops. So this is it actually learning and training. So there's going to be 8 epochs. So this is going to take a minute. But here the model is learning, and we can see the loss. Yeah, what time is it?
It's fine. 10 minutes.
Perfect. That's fine. You're missing the best part. Okay.
So this is the notebook from the report.
No, I made this.
Yeah.
So on GitHub, they have a Jupyter Notebook code space template that you can just download. So like they have an example problem here. And I'm not gonna take credit for this. I used some AI to help me because AI understands this stuff very well, and I understand it kind of well. Like I understand what everything is doing, but could I write this? Could I have the loss dot backwards function where we step into the like we take small steps in our optimization function? Like, so I used some assistance
Copilot takes control a lot of the time.
on GitHub.
Yeah,
It does.
like I was just writing an update function.
It's
And
annoying.
it keeps like telling me like what the next line is gonna be.
You can turn it off. But so okay, we generated a loss for each epoch, and we can see that it actually gets lower with each epoch. So it is learning. So it's done, the model is trained. So now we want to analyze our losses per epoch. So in each epoch, we're looking at 489 molecules. So obviously there's going to be lots of, and we start with randomized weights, right? I think we're all familiar with this. And so like, we're going to have lots of like stochastic losses that we don't learn too much from. But over time, we're going to recognize that pattern, and it only decreases by like a magnitude of 0.1. But with more epochs and a more complex model, which I'll talk about later, this could really be like optimized. So our model accuracy is 77.58%, which I actually like better than when it was 90%, because that was just saying everything is non-toxic. And so it predicted toxic correctly with 24%, obviously, that's the converse. And so now let's see what it's actually doing. This is my favorite part, explainability. So this is like the benefit of machine learning as well. We can see what's going on in here. So we had two hidden layers. And we said in an ideal world, the first layer is going to couple elements together. The second layer is going to couple couples together into like structures and chains. And so what do we learn? Like absolutely nothing. I don't know if you can read this, you're a genius. So that's that. And this is pretty much what I just talked about. But now let's actually look at what it's done. This is just way more graphs. So molecule 1, what did it label it as? It predicted non-toxic, it was toxic, so it's wrong. All the other ones, it predicted correctly, non-toxic. This is what I was saying. A lot of the data is skewed towards non-toxic, so it's gonna guess non-toxic most of the time. Here it guessed toxic and it was correct. So in this, for this molecule, it was actually pretty accurate. For this one, it's actually pretty accurate. It guessed toxic, which is good, but it was actually non-toxic, unfortunately. And this one, I think, was terrible.
There's a well-known problem with this.
What?
Which is it's called the structure activity flow.
Yes.
What that means is if you modify the structure just a little bit, you can make the molecule become toxic.
Really?
So,
I don't know about that.
so you can't just rely on the structure.
Really?
That's the problem.
Okay.
There's lots of things that's maybe not toxic to people, but toxic to dogs or something.
Yeah.
It's true. Grapes. Okay.
Thank you.
Have a good one. Yes. Okay. And so this is our confusion matrix of our guesses pretty much. And this isn't too important either. It's just more like understanding the data and how accurate we were. I swear I had more. So this is takeaways from the project, but the most important part, I'm not sure what happened to my graph. Oh, here it is. Okay, so going further on explainability, we want to ultimately we want to identify what elements contribute to toxicity. So this is what this has done, and it's labeled them in order of priority. And it's just looking at like the weight data and understanding it like better than a human can. But I mean, yeah, that's my presentation. Can I take a picture of this for my LinkedIn?
Yeah.
Yo, would you want to take a picture?
Yeah.
Thank you, sir. What looks the best?
Yeah, that thanks, that was like,
Yeah.
the more accurate of it.
Yeah.
That was all right.
Oh, thank you.
Let's go. Thank you.
Yeah, Lucas, you did an excellent actually. I like
Thank
it. I actually learned a lot.
I stayed up all night for this.
Yeah, wow, congratulations, yeah.
Oh, yeah.
You did an excellent job, yeah.
Thank
So you actually, those program, you actually, write it yourself.
Yeah.
And but you grab the data from some source.
Yeah, that was all already predefined. Like this is a problem you could probably find on GitHub.
Yeah.
This is like my layman understanding of it. Even though this is like complicated, like this is using, so okay, yeah, I want to talk about how we could improve this model. So we talked about before, like connections can have different meanings, right?
Yeah.
This can be double bonded to this, and we want to recognize that with importance. So nodes should really have more data associated with them because chirality, like bonding, they all influence the toxicity, and we're just not accounting for that.
So what is the adjacent matrix here?
For this one,
Yeah, so each of these graph has a different adjacent matrix.
yeah.
And then you have each of these you have different you run it separately or put it all together into a huge node matrix.
Yeah, so it's all separate.
It's separate.
Yeah, so we look at each model individually and we classify. So that's kind of going back to the inductive like nature. So we've looked at previous molecules, we've trained the model, and then we can look at this new molecule and classify it.
Okay, thank you.
So yeah, if we did want to improve it, we would include more data in each node, like chirality, type of bond. We could include data in our edges, like yeah. And then obviously we could have more layers. We could use different algorithms for like data aggregation and back propagation, which is loss minimization. And this is wrong. It was less successful.
So are those coefficient matrices omega k? Are those sparse matrix, or are they just at the entries could be a lot of entries?
So they are not sparse.
Yeah, okay.
You're talking about
No, each layer you have an omega k, right?
Yeah, I wonder about the.
In the convolution matrix, in the convolution network, usually those are sparse matrix. But here probably because we introduce adjacent matrix, it's kind of like these graph neural net this graphic convolution network is you introduce an adjacent matrix so that each of these linear transform the matrix would have this special form that has an adjacent matrix to the right of the each matrix, the node matrix. So it's kind of like have this kind of uniform form. Transformation matrix has this kind of like particular form. In a sense, it probably represents that this is kind of like if you write it differently, it's kind of represent a sparse matrix.
Yeah.
You are using some information adjacent matrix all the time in all your layers. The adjacent matrix is the same thing in all your layers.
Yeah, it is the same in all the layers. So I do see what you're saying. I'm not sure, but I think, yeah, I think it might. It doesn't. It shouldn't really matter if it's sparse.
I mean, it's usually sparse is more efficient, but because you wrote, you're right, you have your node embedding matrix. This is actually E times N dimension. So that
Yeah.
Okay, thank you very much,
Yes.
Lucas. That was an excellent slide. I also have
Me too.
yeah, all right, okay.
Thank you.
Yeah, let me remind everybody that on Monday, so our next machine learning seminar is not Thursday next week, it is on Monday. Monday we have the Benoit Darine from Google who will speak on why this neural network can find an easy solution. So okay, so do come to the
There's no meeting on.
no meeting on Thursday, but the meeting is on Monday. Okay, so we have an outside speaker. No, not here. It's at Armitage 124. Armitage 124 in the email. Armitage 124. Okay, Monday 11:20 different time as well.
Yeah.
11:20 to 12:20 during the 3 hours.
Okay.
So that is yeah.
Certainly.
Maybe we can do it.
Okay.
Have a good weekend.
That you could feel.